Alright, in this video we're going to prove one of the distributive laws for sets, that A union B intersect C is equal to A union B intersect A union C. Proof. Okay, we're going to show that the left-hand side is the subset of the right-hand side. We also show that the right-hand side is a subset of the left-hand side. So we will show that the left-hand side is a subset of the right-hand side. And we will also show that the right-hand side is a subset of the left-hand side. Okay, so first proof, that A union B intersects C is a subset of A union B intersect A union C. Okay, suppose that X is an element of the left-hand side. By definition, X is an element of A, or X is an element of B intersects C. So before I start writing down the formal proof, I'd like to draw a picture to kind of illustrate what's going to happen with the proof. So here's our set A, here's our set B, and here's our set C. Okay. Now, so the left-hand side, A union B intersects C. So B intersects C is going to be this part right here, and then we're going to take the union with A. So that's the part of the picture that I care about. Okay, now there's two parts. Here's case 1, case 2. If X is in A, then clearly it's going to be in A union B. So if I pick a point X, then here's A union B, and clearly it's inside of there. Also, the point X will be inside of A union C, and so it'll have to be inside of both of these. So that's going to be how case 1 works. So case 1. Suppose that X is an A. Then X will also be an element of A union B, and also X is going to be an element of A union C. If X is in A, then clearly X is going to be in this bigger set, and also X will be in this bigger set. Therefore, if X is in both sets, then X must be in the intersection of those two sets. If it's in both sets, then that means that it's in the intersection. And so that shows that if X is in A, then it's in here. The other case is that if X is in B intersects C. So case 2. Suppose that X is in B intersects C. Okay, again, let's refer to the picture. Suppose that I have a point X here that is in B intersects C. Again, this point X will then be in the union of A and B. Also, this point X will be in the union of A and C. And so it'll be again inside of both unions, and therefore in the intersection of those unions. Then X is in B, and X is in C by definition. Since X is in B, we have that X will be in the bigger set A union B. Also, X is in C, so both of these things happen. X is in B and in C. So we have that, and so we have that X will be in the bigger set A union C. So if X is in B intersects C, that means X has to be in B and hence in A union B. X also has to be in C and hence in A union C. Therefore, X must be in the intersection of both sets, A union B intersect A union C. So, in either case, X must be an element of the right-hand side, A union B intersect A union C. And so we're done. Okay, so that proves the subset in one direction. Let's now take a look at the subset in the other direction, that A union B intersect A union C is a subset of A union B intersects C. Okay, so suppose that X is an element of A union B intersect A union C. By definition, X is an element of A union B, and also X has to be an element of A union C. If it's in the intersection, it's got to be in both sets. All right, now we're going to have two cases here. The cases of this one are going to be a little bit different than the cases in the previous one. Case 1. I want to see if it's in this thing. So case 1, suppose that X is an element of A. If X happens to be an element of A, then clearly it's inside this union. Then X will also be an element of A union anything else. And so we're done. So that's the easy case. If X is an element of A, then clearly X will be an element of this right-hand side. Case 2, suppose that X is not an element of A. Okay, so what has to happen here? Since X is an element of A union B, we conclude that. So X is not an element of A, but X has to be in A union B. So if X is in this union, but it's not an A, then the only possibility left is that X is in B. Also, X is an element of A union C. So X is in this union, and also X is in this union. So if X is not an A, but X is inside of A union C, then it has to be that X is inside of C. And so X is a union of C since X is not an element of A. So if X is not an A, we can conclude that X is in B and X is in C. Since X is in B and X is in C, we have that X is inside the intersection, B intersects C. And if X is inside of this set, then it's going to be inside the union of this set plus anything else. So I can take the union of this with anything else, and X will still be part of it. So therefore, X will be in A union B intersects C. I know it's in this set, and therefore if I take the union with anything, it will be still in that set. Okay, so case 1, we have that if X is an A, then X is in this union. Case 2, if X is not an A, X is still in the union. So in either case, X is an element of A union B intersects C. And that ends the proof. So we've established that the left-hand side is a subset of the right-hand side. We've also established that the right-hand side is a subset of the left-hand side. Before closing this video, I will certainly concede that this is more complicated than some of the other problems in this set of review exercises, especially because this was a proof by cases. So X was an element of this union, so we had 2 cases to check. Here the two cases were kind of easy. You just follow your nose. X is in A or X is in B intersects C, and then follow your nose. Here the two cases were far from obvious. Suppose that X is A. Why did I know to write this? Well, I knew to write this because I knew where I was heading. If X is in A, then clearly it works inside of this. And then if X is not in A, then I kind of followed my nose to show that it had to be in this set. So I will certainly concede that the cases in this second part are far from obvious. And the only reason I chose these two cases was because I kind of knew where I wanted to end up.